All right, so today we're going to talk about section 2.1, which is an introduction to linear functions. And we're going to kind of get the footing that we need for the rest of the chapter because chapter 2 is all about linear functions and linear equations. So let's kind of talk about some generalization before we begin, and then I'll talk more about the definition of linear functions as well as what is a function and stuff like that. So we are given these patterns, and we want to kind of talk about what this means for us. So we have this shape here, and then we're given this next shape, and we want to draw the next shape in the pattern given these two shapes. So if we look at this one, we both see that they start off with a square in the center. So we can already label that as the first square. And then we want to kind of count up all of those squares around. So we have 1, 2, 3, and 4 for the first one. And then we have that same pattern, 1, 2, 3, and 4. But then we also have another layer of those. So we have 5, 6, 7, and 8. So you may be thinking that from this pattern, this first initial one, so we'll call this figure 1, F1, and this one being figure 2, F2, the change was it added on an additional 4 blocks, right? And we can see that. It started off with the center block and then 4 on the outside, and then the next one gained an extra 4 given this previous figure. So essentially, this pattern is figure 1 plus 4 on each one of those sides. So then we can kind of assume that our third one, figure 3, is going to be just like figure 2 plus an additional 4 pieces. So we'll start off with our basic piece that we had before, figure 1. We'll add on those additional pieces on the edges, figure 2, and now we'll add an additional side, figure 3. So again, from figure 2 to figure 4, we increased by another 4. Now you may be thinking, oh wow, well this is just in increments of 4. So if we wanted to draw or write the generalization or the formula that each one follows, it's going to have a plus 4 in it. Well, let's see if we can follow a trend. So for figure 1, we had 5 square shapes, right? We have the center one plus those 4. And then for figure 2, we had the previous amount plus an additional 4. So that gives me 9. Now for figure 3, we had the previous one, figure 2, plus 4. So 9 plus 4 gives me 13. And so I can assume that from each one, I'm going to be adding another 4. Right? I'm just keep going and going and going. So if I were to calculate the fourth one, that's going to give me a 13 plus 4, which is going to give me a 17. And then if I wanted to add another 4 to get my figure 5, I'm going to add another 4 to the 17 to get 21. I would then get 25 for 6. 1 for 10, right? We have to kind of figure out a formula, right? Or we're going to add the missing ones in between. So before we calculate the 100, the 10th, the 50th, the 100th, let's try to find a pattern. So each one we know is increasing by 4. But if I were just to start off with this one, and we have n plus 4, right? If that's what we want to think for our general term, we realize that this isn't going to really help us. For figure 1, for the first one, if I plug in n equals 1, I get 5 as the output. That works. That satisfies this first one here. For the second one, I need to put in n equals 2, and I get 2 plus 4 is 6. That does not work. So when we see terms increasing by the same rate, that number does not get added on the end. In fact, it gets multiplied onto the end. So 4n is actually going to be something we want to look at. Now, again, this won't really help us if we try to use just this general term, right? We know that the n plus 4 doesn't work. But 4 times n, if I plug in n equals 1, I get 4. That does not help us as well. What am I off by? Just a plus 1. So let's assume that my formula is 4n plus 1. Then I will get, for n equaling 1, 5. If I were to test n equals 2, I get 8 plus 1 equals 9. Check. So the general formula for these figures is going to be 4n plus 1. That is the general formula. And we found that by finding how much each term increases by, multiplying that on the end, and then adding whatever the difference is. So we can now calculate the 10th most. That's going to give me 41. The 50 most, right? Typing in the 50, that's going to give me 50 times 4 plus 1. That's going to give me 201. And the 100th, which is going to be 101. And my nth is 4n plus 1. So this is called recursion. When the next term bases itself off the previous term. So essentially what we have here is a sequence of numbers, right? They each increase by 4, but the previous one is in the second number. So for example, 9 was the 5 plus 4. 13 is 9 plus 4. So they all kind of build off of the previous term. And we saw that here, right? We started with this base pattern, and then we just kept adding on to the base pattern. So this base pattern was in each one of these flowers or figures that we have. So we call this recursion because it uses the pattern beforehand. So the tables will help us find the patterns, and in the right column, this is how the pattern's growing. So this is our figure number or our input, and this is the number of squares in the shape, which is our output. And we did this before in section 1.1 at the beginning of the semester where we had those input-output tables. Those were what we were kind of trying to get you to realize that those are the definition of functions. Functions take an input and they produce an output. They're like a machine. So for all of these, right, the figure number or the n number, n equals, all the way down, this is the input. This is the variable that the function relies on. And this is the output. So the key for finding the pattern, which was to figure out what the pattern was, and we call this explicit pattern, that's going to be our 4n plus 1. The explicit pattern is the 4n plus 1 because that's the general form of the pattern. So like I said earlier, the rule is not 4n plus 4. It doesn't work. We tried that. It has to have that 4 times n. So, we want to draw the next shape. So this one starts off with a dot in the center, and then it has 3 dots on the side. So we have 1 in the center, and then we have 1, 2, and 3 dots on the outside. And each one of these dots is increasing, right? We have another 3 after we have our beginning one. Same thing over here. We have our center one, right? And then we have this piece, which is all of this pattern before. And then we're adding 3 more. 1 here, 1 here, and 1 here. So given what we just did in the previous pattern, this one should be very similar, right? So for the first input, we get 1. We get an output of that's 4 dots. We get 3. So we have 4 here, 5, 6, and then we get 7. The next one, we're going to have 10. Now notice that they're all increasing in increments of 3 this time. So when we see the increase of 3, we automatically test the 3n part. So given the 3n, right, the multiple of n, we want to test and see, is this formula going to work for our general term? Already off the bat, we kind of know it's not going to because I need to get back a 4 for my figure 1. So when n equals 1, I need to get 4, right? And 3n is not going to give that to us. Plugging in 1 for n is just going to give us 3. So if I plug in 1 here, I need to add 1 to get the 4. So let's make sure that this works for the other 3 that we have. Let's test n equals 2. So that's 3 times 2 plus 1. That equals 7. Okay, cool. Now for the n equals 3, we need to get 10 back. So 3 times 3 plus 1. Cool, we got 10. This is going to be our pattern. 3n plus 1 is going to be our pattern. So if we want to draw the next term in the sequence, right? We want to draw the next one. Let's use what we have here. And let me just delete this. Copy this over. All right, so if we want to draw the next term, all right, so here is my figure. I'm going to make it a little smaller. All we're doing is adding 3 on the end. So a dot on each edge. That's it. That's all we have to do. So then 10, that should give us 13 plus 3. So this is figure 1, figure 2, figure 3, and this would be our figure 4, which was what we had to make. Okay, so we know that there's 4 dots in figure 1s, there's 7 dots in figure 2, there's 10 dots in figure 3, and there's 13 dots in figure 4. We want to continue this pattern, figure out how many dots are in the 100 figure, the 100th figure. So we will simply get here 16, we're going to get 19, now we have 10, that's going to give us 31, plugging in 10 for the n. 50, right, that's going to give us 151. 151, and then for the 100th, we're going to get 301, and then for the nth term, we know that we have 3n plus 1. Okay, so we have this figure now. This is the same idea, except we're starting off with 2, which is different from what we've had before. We've started off with 1 in the center, right? Our center. So this is figure 1. This is figure 2. This is figure 3. And we're tasked to draw figure 4. So we know that we're going to assume that we're using the previous ones, right? And that's what we've been seeing for all of the different ones that we're doing. So for figure 1, we have 2 squares. For figure 2, we have 5 squares. For figure 3, we have 2, 4, 6, and 8 squares. So we have to figure out how many figure 4 is going to have. If we calculate the difference between each one of these, that's an additional plus 3. So that's the same kind of idea we had last time. So we can assume that we're going to have 3n somewhere, but we have to figure out what we're adding because we're starting off with 2. So if I want to draw the next set of figures, I know I'm going to use the previous one and then add 3 squares on either end. That's going to give me 11 because of 8 plus 3. We know that it's increasing by 3. So plus 3. All right, so we have 11. Now we need to figure out what are we adding, or is this term just going to be 3n? The answer is no, right? Because I need to plug in something for n equaling 1, and I need to get 2. So n equaling 1, I need an output of 2. Well, we know that adding is only going to make our n bigger, right? 3 plus or minus something equals 2. Now, the previous problems, we had added everything. Now we want to look and see, what if we subtracted things away? Will that help us out? So in order to get 3 minus or plus something to equal 2, we have to subtract 1, right? And that gives us 2. So let's test 3n minus 1. So 3n minus 1 is going to give me, if I plug in n equaling 2, we get 3 times 2 minus 1 that gives me 5. That works for our second figure, so we can say figure 1 has 2, figure 2 has 5. Now let's test out for n equal 3. 3 times 3 minus 1 gives us 8. That's how many we have in figure 3. Perfect. So I'll put the 8 there. Figure 4 we already know has 11. I think this is our general term here, 3n minus 1. That is going to be the general formula, so we can put that down here. And now we can calculate everything else, right? So we have 14. 3 times 5 minus 1 gives us 14. We can calculate the 6, so 3 times 6 minus 1 gives us 17. Timesing, now we want to calculate for 10. So we get 3 times 10 is 30, minus 1 is 29. 25 times 3, we're going to get 75, minus 1, 74. And now we have 100 times 3 gives us 300 minus 1, that's 299. So our general term is 3n minus 1, and we can calculate that by the figure. Okay, so I think this is the last figure that we are going to draw, and then we'll talk about some other concepts. All right, so we need to figure out the pattern for this figure. So we have figure 1 is going to have 1, 2, 3 sides. So each side / toothpick, whatever you would like to call it, that is how many we have. For the second one, we have 1, 2, 3, 4, 5, 6, and 7. So we have 7 sides. For figure 3, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And for the fourth figure, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 15. So we have 15. So we can see that each increment, right, is growing by 4. And we've seen this before, right? We saw this with the last one, and we've seen it with the same, we're doing the same kind of idea. So let's keep up with this and figure out what the next shape is going to look like. So we know that it always uses the previous shape before it, right? It has that previous shape somewhere, but we know that it's adding on plus 4, right? So we can assume safely that the next figure will be 19 sides or 19 toothpicks. But we need to figure out like the general formula. So we know that when we're adding by 4, that goes on the n. So 4n, and now we have to figure out what we're adding or subtracting by. So for n equals 1, we're expected to get 3 out. Well, 4 times 1 gives us 4. Subtracting 1 gives us 3. So let's try minus 1. Will this formula hold for the other terms that we already have? So let's test for n equal 2. We should get 7 back. So 4 times 2 gives me minus 1. That gives me 8 minus 1 gives me 7. Perfect. N equals 3. Should give me 11. That gives me 4 times 3 minus 1. That's 12 minus 1 gives me 11. And we'll test for the last one, which is n equals 4. 4 times 4 minus 1, that's 16 minus 1 gives us 15. Perfect. It looks like our formula is going to work. So we can put our 4n minus 1 down here. And so now let's draw that last figure 5 that they asked us to draw. So I'm going to reuse the previous piece and just paste it down here. Make this a little bigger. I think that's good. And so we need to draw an additional 4. So I'm actually going to copy this one and paste it down here and see if I can get this to overlap a little bit. See if we can get this to look right. See if we can just get this like that. Okay, perfect. So there's the plus 3, and then I just have to draw another one here. So this would be our figure 5 because there's going to be this plus 1, 2, 3, and 4. So if I want to highlight that I added those, 1 here, 2, 3, and 4. That was that plus 4 from the previous term. All right, so we know now that term 5 is going to be 19. And so now we can keep going with this idea, right? The same that we've done beforehand. And we can continue to add them all up, right? So we can use the formula to calculate the 6. So that's 4 times 6 minus 1 gives us 23. 10 is going to give us 40 minus 139. 25 times 4 gives us 100, minus 1 is 99. And 100 is going to give us 400, minus 1 gives us 399. So that's going to be how many toothpicks are in our shape for any figures we want to do in the future. Okay, so we want to construct a graph using the first 5 entries from the table above and determine appropriate scale and label the horizontal and vertical axes. So let's talk about what the purpose of this is. So we have our figures here, right? We have our figure numbers and we have how many toothpicks are in that shape. Now, this way of visualizing that graph, right, we have them arranged in a certain manner, is very nice to look at, right? But it doesn't really show us clearly if it's increasing or not. Now, obviously, we can see that it's increasing because of the general shapes, but if it was arranged differently, right, that might not be immediately obvious to us. And in mathematics, right, we want to notice trends. We want to notice what's going to happen in the future. And so graphing something like this or drawing pictures like this to show growth, because that's essentially what's happening. As the figure gets bigger, the toothpicks amounts get bigger, right? As you continue drawing more figures, you have more toothpicks. But we want to make that obvious to the reader or somebody who's reading our math work that this is the case, that this is growing. So what we want to do is take this figure chart that we have here, and I'm going to copy the first 5 entries. And we're going to just copy that. Oh, we want to copy that, not cut it. So we want to take all of these and we want to paste it over here. I'm going to see if it does not want to paste. Okay, so we have to construct a graph. And by graphing, again, it's not really clear about how we want to graph this, but we can graph somehow that we want to. So we know that our first one was n. So we have n values 1, 2, 3, 4, and 5. That's what we're interested in. And then we have our output values here. And so we knew that was 3, 7, 11, what was the next one? 15 and 19. Okay, so that's what we want. Now, I'm going to start at the bottom of this graph here, and I'm going to call this piece here 0 in terms of my output. So here's 0, or I could write it here, 0, okay? And then this line here going up, I'm going to call that my output. And this is going to be my n chart. So we'll have 1 here. I think I'm going to skip every other just because. So I'm going to start with 1. I'm going to draw 2 here, 3, 4, 5. Okay, so I've labeled my ends. Now I need to graph my corresponding outputs. And so my first output, I'm going to use red for this. My first output was 3. So I'm going to use that same idea. I think I have enough space to do by 2s. So 2, so this is 1, 2, and 3. Let me see if I have enough. 4, 5, 6, 7, 8, 9. Okay, I definitely don't have enough to keep going. So we'll just use this as 2, 4, 6, 8, 10, 12, 14, 16, and 18. So each one of these little squares is going to indicate 1 space. Okay. All right, so for the first one, for n equaling 1, that's here, we're going to plot 1, 3. So we'll go up 3. So there's our first spot. That's our first value in this input and output chart table that we have. So input and the output. Okay, the next thing, 2, 2 and 7. So we have 2 here, and I'm going to go up. 7 is going to be here in between the 6 and the 8. So 2, 7, that's going to put me right here. Okay, perfect. Now I want to graph 3, 11. Plot 3, 11. 3 and 11 is going to be between the 10 and 12. So 3 all the way up to 11 here. 4 is going to give me 15. So 4 all the way up. 15 is here between the 14 and the 16. My 15. And then we have 5 and 19. So 5 all the way up to 19 over here. Oh, that's not right. It's over here. All right, that one, I have to move this dot over 1. Okay, so those are all the points. And so we could label them, right? This is 1, 3, right? N equals 1, my output equaling 3. 2, 7, my input equaling 2, my output equaling 7. 3, 11, 4, 15, and 5, 19. Now, this is helpful, but not completely helpful, right? We can see the points, but we're not drawing anything, right? Now, what I want to start off with, right, is taking here, and I want to connect all these dots to see what's happening. And if I kept going on, it looks like it's following that trend line, that line of increasing. Now, it's increasing in the output way faster than it's increasing in the input, right? We can see that the ends are only getting so big, but the outputs are getting really big. And that was coming from that formula, that 4n minus 1, right? And that's what we had beforehand, 4n minus 1. And that's the plot. This is what our plot looks like. And this is really clear to the reader that the output's increasing faster than the input. And that's why we have this faster growing line, because of that reason, right? We notice that it's growing faster. So this is a line, right? That's the shape that we got. And that's why we're calling this 4n minus 1 linear. And so what that immediately means to us is because it's growing like a line, right? We just plotted a few of those points to kind of give it a visual to what we're looking at, and we can see it's a line. It doesn't look like any other shape. All of those points are growing in an equal and a consistent manner. So that's the whole idea for Unit 2, is going to be talking about how we have some linear equations, linear functions, and what does that mean for us, and like the definitions. So we're going to go over exactly what linear equations are the next section, but the idea that I want you to take away from this specific part of the lesson is that linear indicates lines and functions are those input output tables. Functions are those input-output tables that we had at the beginning of the semester. If you want to refresh, go back to section 1.1 to refresh those input-output tables. But that's kind of what I want you to gain from this piece of lecture, section 2.1, was just that linear indicates a line and that it's growing. The equation or the graph is growing at a consistent rate, right? It's growing by those increments of 4. We can see that here. And we'll talk more about that, what that means. But for right now, we just want to know that linear functions are linear, meaning that they grow at a consistent rate, and that they have an input and output table. Linear also indicates that this n here, looking at the 4n minus 1, this n, highest power power is 1. It's n to the first power. And once you get higher with exponents, it's no longer a linear function. It's not growing in the same rate. Okay, so that is all for the linear portions, and back to those figures and stuff like that. So we want to go back to talking about some exponents, fractional and negative exponents, and how that's going to help us. So we've talked about exponents in this course, and we talked about fractions with exponents, right? We talked about square roots of like fractions. I think we had something like 16 over 25, the square root of 16 over 25. And we had square root 16, we had negative square roots, right? Negative 25. We have stuff like that. But now we're going to talk about other forms of exponents, and we want to talk about what these radicals actually look like in exponent form. So we have 10 to the 5th is just 10 times 10 times 10 times 10 times 10, right? 5 times. So 1, 2, 3, 4, 5. And that 5 is corresponding to this power here. Same thing with 10 to the 4th, right? 4, 10 times itself 4 times. 3, 10 to the 3rd. That 10 to the 2nd power times 10 times 10. And if we want to do these, we get 10,000 here. We get 1,000 here. We get 100 here. We're ditching a 0 every time we go down. So 10 to the first power is just 10 times itself, or just 10 one time. So we get 10. Now 10 to the 0 is an interesting thing that we want to figure out. So what do we think that would be if we're ditching a 0 every single time? So we ditch a 0 here, ditch a 0 here. We're just cutting off a 0. We only have one more 0 to get rid of here. So that's going to tell me that this next value would just be 1, which indicates that 10 to the 0 power is 1. Okay, that's fine. Now, we want to do 10 to the negative 1. Negative exponents are interesting, but we want to try to figure it out from this table before we actually formally define everything. So if we continue with this trend where we're ditching zeros, getting rid of the zeros, well, we don't have any zeros now. But what I want to do is actually start introducing decimals. So 10 to the negative 1, right? This answer is going to be 0.1. I'm introducing zeros to the left of the decimal place. So if we think about this having a decimal place of here, of 1.0, I want to move that decimal. I want to move the decimal over because of that negative sign, moving to the left. And think about scientific notation. We should have seen that before, right? In chemistry in high school, or in some type of math earlier on, or even in your everyday life. Sometimes you see significant figures and scientific notation. So what does that look like for 10 to the negative 1? Well, it would be, if we have a decimal, that's going to be 1 over 10, right? This decimal is converted to 1 over 10. And we can type it into our calculator and figure that out. Now, if we start over looking at the value, we're going to move that decimal place again to the left. So that's indicating that I have a 0.01. I'm moving that decimal again. Well, that is 1/10 times 1/10. Again, looking at our value table, we're going to want to do the same thing. Moving that decimal, so I have 0.001. And again, that's going to indicate 1 over 10 times 1 over 10 times 1 over 10. Notice how they all went from positive and normal tens to fractions. So, our general rules when we have exponents, any number to the first power is what? Well, let's do some examples. 5 to the first power gives us 5. We saw that 10 to the first power gave us 10. So we can safely assume that n to the first power is going to be n. N to the 0th power. Well, when we were doing our placements of 10, we noticed that it turned into 1. And we can figure out that if we think about it, n to the 0th power is always going to be 1. And I can show you this proof and show you kind of why this works. I'll show you in a second. But for right now, we just want to memorize that this n to the 0 equals 1. N to the negative m, look back at these sections of our chart. That was indicating that whenever we have some number to the negative power, notice that it flips itself in a fraction. So whenever you have n to a negative exponent, it always turns into n 1 over n to the m. It just flips and crosses the fractional bar. So let's do some practice with simplifying these expressions, and then I will show you how this n to the 0th works. So we have 5 to the negative 2. That we're going to want to rewrite as 1 over 5 squared. We know what 5 squared is. That's 25. So this is our final answer, 1 over 25. We have 3 to the negative 3 times 5 to the 0th power. Let's calculate. So we have 1 over 3 to the 3rd. We're converting this first piece. Now we want to multiply that by 5 to the 0th power. Well, we know from our rule beforehand that anything to 0 power is just 1. So our final answer is 1 over, and we know what 3 to the 3rd power is, 27. That's going to be our answer for that one. Okay, so for this one, we have to do the inside first, and then we'll figure out the outside. So negative 2 to the 1st power, it's just going to be 2 using our rules, times 3 to the 0 power is 1 to the 4th, negative. Now, we have to do the insides first. That's going to be 2 to the 4th. This one is very tricky. This is not saying negative 2 to the 4th. That's not what this is saying. This is saying the negative of 2 to the 4th. Well, what's 2 to the 4th? 2 times 2 times 2 times 2 is going to give us 16, right? 16, yep. And then we keep the negative. That is the answer for this one. The negative is last. We do the exponent first. This one is saying negative 2 times negative 2 times negative 2 times negative 2 gives us a positive 16. This negative 2 to the 4th does not equal negative 2 to the 4th. They're not the same. You need to be very careful with your negative placements. Okay, example 6. Rewrite the expression using only positive exponents. Well, we don't know what x, y, z are, what they are, but we know that we can flip across the fractional bar when an exponent is negative. So looking at the top first, we have that x to the negative 3rd. I'm going to put that in the denominator as x to the 3rd, immediately moving that positive. Y squared is the same because it's positive. Now we look at the denominator. Z to the 3rd is fine. Now, if the negative exponent is in the denominator, all that it has to do is flip the fractional bar again and come back up. So we can say we have r to the 4th in the numerator. We just move it up. So that is our final answer. All right, let's talk more about this n to the 0. So what this basically is saying is that, remember our rules of exponents is that we add exponents. Well, agree with me that n to the 0 is n to the 1st times n to the negative 1. Remember, we add exponents when we multiply, and we did this last section. So if we were to combine this, we add the exponents and we get 0. All right, perfect. Well, that's saying n times n to the negative 1. Well, we know that n to the negative 1 has to cross the fractional bar, so we get n times 1 over n. Well, don't we agree that the n's would just cancel in this instance? That's all that we would have. So if we were to do the simplification, the n's will cancel and we're just left with 1. And that is why n to the 0 power is equal to 1. So that's a cool little trick here. All right, the last concept that we're going to talk about is the square roots. So remember, we did all those square roots. We have square root 16 over 25, square root 16, square root negative 16, blah, blah, blah. We did all those things. Okay, so think about square roots, right? We know that they're taking the root, or we're finding the number when multiplied by itself is the root, right? That's what we're finding. So what they're saying here is that if you think about it, x to the 1/2 power times x to the 1/2 power, we add those exponents and you get x to the 1 is x. Okay, cool. Whenever we have square roots in that we're looking at, square root of x is written as x to the 1/2 power. This is technically what a square root is in a power form. So, for example, 7, they're asking us to rewrite the square root of 100 in exponential form, root form, as the root of a square, and then simplify. So they want us to use this formula here to write 100, the square root of 100. Okay, that's fine. So we're going to reverse it. So 100 is equal to a 100 to the first power. So I'm just using this piece here, and I'm working backwards, which is going to be, we need to find the square root of 100, which we know is 10, right? We know that's 10. But we want to write 100 to the 1/2 power times 1/2. We can write this as 1/2 plus 1/2. That gives us the 1. So that gives us 100 to the 1/2 times 100 to the 1/2. Now, we have to figure out what 100 to the 1/2 is, right? What is that? That's square root 100 times root 100. That gives us 10 times 10. So we figured out that the square root of 100 equals 10 by using this long method. So let's actually do some practice and figure out. 49 to the 1/2 power. Well, we know that a square root is the 1/2 power. So that's a square root of 49. We all know how to calculate square roots. Gives me 7. 49 to the negative 1/2 power. Well, let's ignore the 1/2 for now and figure out what's 49 to the 1/2 power, or to the negative power. We have to cross our fractional bar. So that's 49 to the 1/2 power. Cool. Now we can calculate 1 over the square root of 49 by using our rule here. That gives us 1 over 7. All right. So practice 9. When we have a fraction to the 1/2 power, we take the reciprocal. So for this one, since it's 1/4 to the negative 1, we want to make that exponent positive. We do the reciprocal, 4 over 1 to the 1 power. Whenever something's to the 1 power, it's just itself. It's 4 over 1, which is just 4. Okay, let's do the next one. 1/2 to the negative 3 gives us 2 over 1 to the third equals 2 over 1 is just 2 to the third. That gives us 8. All right, this one. Well, this has two numbers, and they both have the one has a negative. So we want to take this one and move this 2 to the negative 2 down in the denominator. So I have 1 over 2 to the 2 times 5 to the 2. Well, let's calculate each one. 2 squared gives us 4. 5 squared gives us 25. This gives us 1 over 100. So the answer is 1 over 100. All right, D, 36 to the negative 1/2. That gives us 36. Now, the first thing you want to do when you are calculating whole numbers, right? We want to write this as a fraction with a positive exponent. So that's 36 to the 1/2. Gives us 1 over the square root 36 is 1 over 6. 1/6. Perfect. All right, so that is all of the lesson 2.1. It's a lot of content. I recommend that you practice the problem set or practice all these problems here. And I will post an additional exercise sheet for you all to complete. All right, if you have any questions,